Okay, I will talk now on PN junction. Actually, I recorded like nearly more than 1 hour of video, but then there's no voice. There was an error, so I had to record it again. So be patient with me. Okay, so basically, no, wait a second. So PN junction. So PN junction just means that you have a P-type material and the N-type material, okay, semiconductor, and you join them together, okay. So before that, if you remember the the energy band diagram of of P and N material. So this is the so let's assume both are silicon but dope P and N, okay. So it means that the energy band gap is the same, so 1.1 eV, 1.1 eV, and this is the conduction band, this is the valence band, conduction band, valence band, okay. And the Fermi level for the P is close to the valence band, and the conduction band for the N, the Fermi level for the N is close to the conduction band. So this we discussed why it was like it is like this before. Now what happens is you want to combine these two. You not combine, put it together. So if I were to draw this, so now we'll draw like this. Okay, so this P is N. Add no bias, so I will start with 0 bias, meaning I didn't put any bias or voltage to it. Okay, so what happens is, if you remember, so now we'll talk about what happens inside a PN junction structurally. Okay, structurally, because later there will be another video later, you should be able to explain how the PN junction works using energy band diagram. So the one that you'll be using for your assignment is the one in the using energy band diagram. So this is just like, because this is easier to understand compared to the energy band diagram, so I will start with this. So P and N, basically you have P, you have majority holes, and you have a lot of electron, right? And then remember, so at the N side you have a lot of electron, but you have very little electron at the P. You still have some electron, but the electrons are minority. While for the hole, you have majority of a hole at the P, but at the N side you have minority holes. I mean, you have hole but very little. So can you see now there's a, what do you have? You have concentration gradient, or difference in the concentration, difference in the carrier concentration. And remember last time we talked about drift and diffusion current. Okay, remember diffusion is due to the difference in concentration gradient. So what happens now is, now we can see there's a what do you call it, concentration gradient. So what happens is the hole now will diffuse to the N, and the electron will diffuse to the P, right? Because the electron wants to go where there's no electron, holes will like to go where there's a lot of holes. So okay, then what that's happened, so it means that the first thing that will happen when you put a PN junction together is diffusion current. Diffusion, and therefore you have diffusion current. Okay, so does the diffusion, so all of the electron here will go to this side and all of the hole here will go to this side, yes or no? The answer is no. Why? Because at the, now I need to padam sikit, need to rub something. So because at the junction, this is called p-n junction, right? So at the junction here, when the electron diffuse to this side and hole diffuse to this side, this electron, free electron, will meet free holes over here, and this free hole will meet free electron over here. So what happens when free electron meets free holes and free holes meets free electron? Last time we discussed, it means that we have recombination. Okay, when number free carriers meets free holes, or free carriers meet each other, so you have recombination. Right, sorry. So recombination will occur. So when recombination occur, so what is recombination? When recombination occur, you are losing free carriers, right? So this side, so this side, you'll be losing. So there's to be a region here. Let me draw the region blue. Sorry. Okay, so it's detecting my palm. So this middle here, where the recombination occurs, you are losing free carriers. So imagine an atom. So if this atom, which is neutral before, lose one electron, okay, what happens to it? It becomes ionized atom or charged atom. Ionized atom. Okay, so it means that at this region where recombination occur, you are left with ionized atom. So on the p side, okay, on the p side here, where the atoms are losing free hole, the atom becomes negatively charged. Okay, because it loses hole, it becomes negatively charged, and at the end, where the atom are losing free electrons, the atoms becomes positively charged atom. Okay, Okay, so now when you have recombination, then you are actually creating what they call it, depletion region. And this depletion region is this region here where you have the ionized atom. Okay, and it occurs due to the recombination. So now if you look at this area here, the depletion region is like a battery. If you go Google battery, how it works, basically you have a lot of ionized atom. So it becomes a battery. This is positively charged, this is negatively charged, and therefore you also have, remember last time we talked in the class, when you have voltage and you have distance, you have electric field. Electric field is just the voltage divided by distance. So now you have a voltage across a distance. Okay, this is called depletion distance or region. Okay, therefore you have electric field. Okay, so when you have the voltage across the distance, you have electric field, and the direction of the electric field is from positive to negative, like this, electric field. Okay, so remember, when you have electric field, what do you have? Current. You have drift current. Okay, so now because of the built-in this voltage, I forgot to mention, in the depletion region we have the built-in voltage. Write it properly. Built-in voltage. Okay, so we have the built-in voltage. So this built-in voltage will give rise to the electric field. Once we have electric field, we have drift current. Okay. So drift current basically due to the voltage. So if you look at here, our p-n junction over here, the hole will like to go to the so wait a second. Okay, now we want to talk about the PN junction at fault bias structurally, how it works. So basically, basically this is the PN junction, fault bias. What happens is the fault bias, this is the PN junction, the diode symbol, right? This is the P, this is N, the symbol. So when you fault bias, it means that you are connecting the P to the positive and the N to the negative. So positive voltage here, negative voltage here. Now, what happens is, remember at zero bias, you still have some depletion region. So when you forward bias, the PN junction, the depletion region becomes smaller. Why? Because now remember we have a lot of majority of holes here, majority of electrons here. Electrons are negatively charged. It would like to go to the positive side, and the hole are positively charged. It will be interested to go to the negative side. So when that happens, right, including the electron holes at this side, so when that happens, so the depletion region becomes smaller. Okay, and number 2. Okay, the depletion regions become smaller because as the hole are going to this side and electron are going to this side, so including the you have more and more free carriers at the depletion region. So now the new depletion region after forward bias will become smaller. So this is the one that I color here is the new depletion region. So the depletion regions become smaller. Okay, and then it means that and once the depletion region becomes smaller, there are lots, because this is majority carrier, so the majority carrier are able to flow. So majority carrier can go to the negative, majority of the carrier of electron can go to the positive. So you have and from this is like from high concentration to low concentration, therefore you have a lot of diffusion current. So at forward bias, if you draw the energy, the IV characteristics, if you remember, current voltage characteristics of a diode, it looks like this, right? So let me draw it properly, like that. Okay, so this is a lot of current in forward bias. So in forward bias, that's why you have a lot of current. At reverse bias, okay, basically is the opposite will happen, whereby this is your P and N junction. Previously you have at zero bias you have this depletion region, right? And before that, reverse bias means you apply negative voltage to the P and positive voltage to the N. So it's like this. So that's a reverse bias. So when that happens, what happens is the depletion region increases. So what happens is, brothers and sisters, here you have majority holes, right, at the P. Here you have majority of electrons. So the holes will like to go to the negative sides, the electron will like to go to this side, and also the electron near to the depletion region will like to go to this side. The hole near to the depletion region will like to go to the negative side. Therefore, for reverse bias, your depletion region becomes bigger. Okay, so depletion regions means you shouldn't have any free carriers inside. Okay, so the depletion regions becomes bigger, and since the depletion region becomes bigger, for this purpose, like if you for first year, you will say no current flows, because it's difficult to overcome this big depletion region. Okay, so the bigger the voltage, the bigger the reverse voltage, the bigger the depletion region. So you apply more reverse voltage, then you have bigger depletion region. So this become bigger. Okay, and normally you say no current flow, but actually there is very small drift current. How? I will explain this using energy band diagram explanation. Okay, basically, so that's what happened when you forward and reverse bias a PN junction.